Hey there. So we're gonna talk about energy in this short little lecture here from Chapter 2. We're gonna cover two main things. We're gonna look at energy and how define it. Talk about its forms, and then we're gonna talk about the first and second laws of thermodynamics, which you may or may not already be familiar with. All right. Let's see here. So this lecture also covers pretty closely the material from the chapter, so you can always go back and review it if you'd like. So first of all, energy. We probably have an intuitive sense of what energy is, but it's officially defined in your book as the ability to do work or transfer heat. So there's different ways of thinking about energy. You can think about the energy that comes from our sun, which we'll talk a little more about, or you can think about the energy found in a wave, an ocean wave, or an air mass moving, the energy locked up in food or gasoline. But most of our energy, as you know, probably comes from the sun. Here's a pretty amazing picture here of the sun, which looks so small here, but it's huge. Some of you might know it more from this picture. Hopefully not. Anyway, so most of our energy does come from the sun. And there are a few exceptions to this. Of course, nuclear energy, energy found in uranium, and other radioactive elements were formed when our planet was formed. And then also geothermal energy, the energy from the heat of our planet, is also not directly from our sun. But everything else really is. So whether it's plant material or air currents, even water flow is from the evaporation of that water. So really it all comes from our sun. And that energy that's coming from our sun is in the form of what we call electromagnetic radiation. And here's the spectrum, or the spectrum of electromagnetic radiation. So that energy comes to us in the form of packets of energy called photons. And those photons also travel in a wave pattern. And so, as you can see here on this spectrum, there are longer wavelengths over here. Oopsies. Longer wavelengths over here on this end here, and then over here we have shorter wavelengths. And this area right here is what we actually can see with our naked eye, the visible spectrum, which is broken down into colors, as you can see here. So the idea is that the longer the wavelength, and the wavelength is measured from one peak to another peak, so the longer the wavelength, what you see over here is a much lower energy, which is shown down here. This diagram is from your book, so you can go back and look at it. And then as you move this direction of the spectrum, you see that the wavelengths get shorter. So here, the wavelengths are much smaller, more like this. And so if you measured that wavelength, that would be a much shorter distance. These are more intense or a higher energy types of wavelengths of energy. And so as you move here, you have more energy than over here. Now this energy can be classified into two broad categories of energy, what we term potential energy and kinetic energy. Potential energy is defined as energy which is stored or not used. So you can think of a lot of examples for this. And again, these are broad categories. There's more specific designations for these types of energy, but so here's some examples you might think of. So we have the stored energy in food, We have stored energy behind a dam, that water, which wants to flow down due to gravitation. And here's another Coyote. The Roadrunner comic strip is defined by different types of potential and kinetic energy, which you'll see in a minute here. So the food that we eat has energy stored in it, and we call that chemical energy. The energy which is trapped in the bonds of that food, and as we digest it, we break the bonds, releasing that energy. The same is true for fuels, things like fossil fuels that we use in our car, for example, is energy stored in that gasoline, and then we break that energy to create kinetic energy, which is the energy of motion. And so, for example, the gasoline that we put in our car, which is potential energy locked up in that gasoline, we then burn it to release the stored energy, to break those bonds, which then helps us produce kinetic energy, or the movement of our car, which would continue if it weren't for all these other things taking place, like resistance, air resistance, and friction of the road, and those kinds of things. So kinetic energy is the energy of motion. Now this is also true of temperature. So as we increase the kinetic energy of a mass, we increase the movement of those molecules, and we increase the temperature. So that's another example of kinetic energy. So we're going to watch a short little clip here to summarize some of these potential and kinetic energies. So that video actually further classified the potential and the kinetic energies into specific types, whether it's gravitational or elastic and those kinds of things. You don't need to be concerned about that. But the broad category is the potential, is stored energy, versus kinetic, this energy of motion. All right. So let's go further and talk just briefly about the laws of thermodynamics. There's two basic laws that we're concerned with, and the first law is that energy is neither created nor destroyed. So energy was formed in the creation of the universe, which is an interesting question in and of itself, and it can not be created, or really it never goes away. It's just transferred into different forms, or transformed into different types of forms. So one example you might think of is wood. So wood has some potential energy locked up in it, in those bonds of the carbon within wood. And as we burn it, that releases the stored energy to produce heat, light, and other stuff from that reaction, so carbon dioxide, ash, and those kinds of things. Now that energy at the beginning of the reaction over here, this energy over here, and the energy released in the form of heat and light, this is equivalent. So it doesn't go away. It just is changed into a different form. Now that brings us to our next law, which is that when energy is transformed, the quantity of energy remains the same, as I just said, but the ability to do work, or the quality of that energy, diminishes. So when you think of something like a piece of wood and what that can accomplish versus the heat that's been dissipated, so what we kind of say is the density of energy decreases. Another way of looking at it is if you have the energy locked up in a gallon of gasoline, that can do quite a bit of work. That's a very dense form of energy. Once you use it and you convert that either into kinetic energy or heat, that heat is a diminished form of energy that now is less able to do work. So we say in the second law that in that transfer of energy, it becomes less dense, less useful. Usually when it's transformed into heat. That is usually the kind of end product of all of these high quality forms of energy, and that'll come back when we look at energy efficiency.